Use the change of base formula to evaluate numerical logarithms. Very often we want to be able to evaluate a numerical logarithm. Now what this means is that we may have a logarithm, for example, log base 2 of 17, and many calculators don't have that base 2 feature. Yet we still want a decimal approximation for that value. And we know 2 cubed is 8, and 2 to the 4th is 16, 2 to the 5th is 32. Looks like this number is closer to 4, a little bit above it. Does that make sense? But I would like to know a better decimal approximation. So what we can do is still use our calculators even though we don't have a base 2. And we evaluate in terms of 10 or e, common logs or natural logs. Now the way we do this is to use a very simple change of base formula that is really very intuitive, and it goes something like this. If I go ahead and write 2 cubed is 8 twice, I realize that the 3 is the same 3 in both representations because it's the exact same equation. So if I look at the equation on the left by just taking the natural log of both sides, and then I bring the 3 out front, and it may sound weird, but then I solve for 3, so I divide both sides by
Natural log of 2?
I can say 3 is the natural log of 8 over the natural log of 2. I think that's a fair sentence.
Right.
Okay. I can go ahead and take a look on my right side and say, gosh, if I switch this to logarithmic form, this is log base 2 of the argument 8 is equal to 3. Now this may be the stupidest thing you'll hear all day, but this 3 is the same as that 3. So what does that mean? You're probably saying, it means you're telling me the obvious, Jay. And my response is, no, you're missing the point. That means this is the same as that. That means that log base 2 of 8 is the same as the natural log of 8 over the natural log of 2. There's your change of base formula. And log base 2 of 8 is just arbitrary. 2 cubed is arbitrary. Basically what we do is we take a look at the log of a base applied to some argument. That's going to be the natural log of the argument over the natural log of the base. Always. And that's what this slide is really telling us. And in fact, when we did that previous problem, when I took the natural log of both sides, that was arbitrary.